Very warm welcome to all the joinees to this webinar. This is another talk in the series of the Industrial Connect program by the IEEE IISc VLSI Chapter. So we are happy to host another eminent personality within amongst us today, and we are very looking forward to the talk. So just before I begin, I would like to make clear to the participants that the proceedings of the meeting will be such that first we'll hear professor talk, and then towards the end we'll be having a dedicated Q&A session where we will unmute you and then you can directly ask your questions, and we will be like happy to have an interactive session with the professor. And apart from that, if you have any questions at any point during the talk, then please feel free to put them on in the chat, and we will be taking up them towards the end. So we will not make any further ado, and just a small introduction to our speaker today. So Peter Baltus, since 2007, professor has been in full capacity in high frequency electronics at the Eindhoven University of Technology, and since 2017, he is chair of the Integrated Circuits Group. Before that, he worked for 22 years at Philips and later NXP in Eindhoven, Nijmegen, Tokyo, and Sunnyvale in various roles, including research scientist, program manager, architect, domain manager, group leader, and fellow in the areas of data converters, microcontroller architecture, digital design, software, and RF circuits and systems. His research interest lies in the domain of low-power wireless circuits and systems. He was born in 1960, received his MSc degree in 1985 and his PhD degree in 2004 from the Eindhoven University of Technology, and currently holds 16 US patents and has co-authored more than 200 papers. So yeah, we are very fortunate to be hosting such a eminent personality in his field, and we look forward to hearing you. So Professor, the stage is all yours. Thank you very much.
Thank you very much for the introduction, and also thank you very much for the invitation. I really appreciate the opportunity to tell you a little bit about our group and our research, and it's great to be able to do that in this way. I'm going to give you a little bit of an overview of what our group has as context, because that helps to understand a little bit better what we're doing and how we're doing it. And then I'll go through a number of projects that are somewhat, I hope, in a more or less logical sequence. But mostly I think it shows the large variation in topics that we cover. So let me get out of the way first and make some room for slides. So I'm going to shrink, and then I'm going to put on the slides like this. So first a little bit about the context of our group. So Eindhoven, for those of you who are not very well versed in geography like I am, it's this red marker in the map of Europe, and for all practical purposes we're next door to the UK. The Netherlands itself, in which Eindhoven lies, is a very small country. It's less than 20 million people, so for most large countries this would count as a city, but of course we're very proud and call it a country. Within that country, Eindhoven has an interesting role because it's in the region that we call Brainport. And in this region, a small part of the Netherlands, about half of the R&D investments in the Netherlands is being carried out. And that's for a large part because it has a rich history, starting with Philips Electronics at the end of the 19th century, starting to do the preparations for light bulbs, and then later extending into more and more areas. And these areas, they grew to cover just about anything. So starting with the light bulbs, they went into vacuum tubes. From there, they went into radios, televisions, then domestic appliances like vacuum cleaners, then ICs for the electronics. Then they went into materials, into fabrication. In the end, they would also produce mattresses and toilet seats and even trumpets and other musical instruments. So really wide range of topics, and that gives, of course, a demand for well-skilled people. And as a consequence, Philips pushed to have a university in Eindhoven, and that's how our university got started. In the meantime, Philips has shrunk, has split off many other businesses. One of the more famous ones is ASML, another one is NXP. And so we have now around Eindhoven a large number of companies, but still mostly derived from Philips, and therefore with people that still know each other to a large extent. And that makes for a very special environment. This is Eindhoven University. It's in the downtown area. You can see it's next to the railroad tracks, so to the central station of Eindhoven. And it's a relatively small university, about 12,000 students, 2,000 scientific staff. And the red marker there is on the EE building that we share with applied physics. And within that building, you can see indicated in red here, there's 2 floors where the IC group is present. On the 7th floor, we have our offices, but of course, much more interesting, on the 8th floor, we have our labs. And if you look very carefully, you can see that through the windows of the 8th floor, you see this shiny mirroring surface, and that's because our labs are enclosed in Faraday cages, because we want to have the benefit of reproducible measurements also for wireless systems. And in an area like Eindhoven, you need to do some shielding for that. This is what our labs looked like on the first day that we opened the building. In the meantime, of course, they don't nearly look like this anymore. That's why we had these pictures taken on the first day. Now it's much fuller and not quite as clean. But we have well-equipped labs, and that's necessary because we believe that, especially for the kind of electronics that we do, for high frequencies, for systems and so on, you cannot stop at doing modeling, calculations, simulations. You really need to implement the systems and to verify that they actually do what they're supposed to do. So what do we do? Well, electronics, right? Integrated electronics. And why is that? Well, basically because electronics is nowadays so important. You cannot really, as a society, even as humanity, survive without electronics anymore. It's present everywhere. It's in mobility, it's in medical stuff. It's in things like communication systems. It's in airplanes, it's in internet, of course, in refrigerators, headphones, and the badge that gives me access to my office, the mouse, a radio receiver, the key to my car, my watch, headsets, iPads, the heating system in our house, remote controls, musical instruments, the card that gives me access to the train, and perfume dispensers, in drones, in passports, in microwave ovens, in laptops, phones, energy meters, cooking ranges, but also, of course, in the most essential piece of equipment that we have in our civilization, and that's the coffee machine. Now, because it's so present everywhere, and it has such a large variety of functions, you have to focus a little bit. And our group focuses on especially the I/O part of systems. Many systems can be thought of as consisting of storage, processing, and I/O, input-output. And we focus mostly on the input-output, the interface from the system to the outside world. And that's mostly analog. So we have mostly analog and mixed signal and RF. And that's also an area where high performance really is important. It immediately impacts the observed functionality and quality of your system. And so that's a really nice area. What makes it so special? Well, basically because, well, it's not really special. It's fun because we're pushing things to the very limit. If you look in terms of accuracy, well, for digital circuits, you need ones and zeros. They don't need to be very accurate. That's one of the strengths of digital, right? There's redundancy there. For analog RF circuits, mixed signal circuits, accuracy is very important. Also for frequencies, we need to work at very high frequencies, and I'll come back to that later. But also power efficiency, or efficiency more general, is important for these circuits. And that makes it a special challenge and something that we very much like. And there's no end to this. There's always a need for systems that work at higher accuracies, at higher frequencies, at better efficiencies. And so that keeps us very busy. I'm typically explain to young students that we have sort of a reversed cycle. Right? Many areas you find a problem, you solve it, and then you have success. But in electronics is already so successful that we start with success, and that success itself creates problems. It creates problems with sustainability, with e-waste, with energy consumption, and so on. I'll get back to that. And so that success of our solutions creates new problems, and as a consequence, we keep busy. Since solutions and successes create problems, we need new solutions, and therefore we have inherent job security in this area. Now, after this, let me give you an idea of the people in our group, so you have an idea about who the people are that are really responsible for all this research. This gives you an overview of the permanent staff, of the scientific staff and the support staff. And you see that on the top line, we have in the green area 5 people that work on RF-related topics, ranging from MRI, which is fairly low frequency, all the way up to microwave, millimeter wave, and terahertz. Marion Matters is our most high-frequent person. She works on terahertz. Dusan Milosevic works mostly on power amplifiers in microwave range, but now also going to car radar and other communication systems in millimeter wave. Vojkan Vidojkovic is a millimeter wave transceiver designer. Irena is in MRI, and Piyush, our newest colleague, is in terahertz and interfacing photonics and electronics. Most of these people actually, and not just for RF, but for the whole group, come from industry like me. They started after doing their masters and sometimes after their PhD in an industrial job. And then it took them some time to realize that you can have even more fun at the university. I was rather slow. For me, it took 22 years. Some people already realized this after 5 years, but this is something that most of us share. We have this industrial background, and that makes it very easy to cooperate with the industry, the many companies that are around us. Completing the list on the top right is Aida Todri Sanyal. She recently joined us. She is a professor in the area of AI and analog implementations of AI. And then on the bottom line, or to the very left, Georgi Radulov. He is in the high-speed data converters. Peter Harpe, he is in the power efficient electronics, so very low power data converters and front ends. And then we have Eugenio Cantatore and Marco Fattori. They both work on emerging technologies. And then we have Renier van Dommelen, who basically supports everything, but is now also working on his PhD. Margot, our secretary, Antonio, our lab manager, and Nathan, our IT support person. So these are the people that are actually responsible for all the research that I'm going to talk about. In addition, we have people from industry that spend 1 day per week with us, voluntary. We don't even pay them for it. And we have 2 people from NXP, 1 from Hanse, 1 from Philips, 2 from Antea, and more people joining us over the next half year as well. This is something that we also very much value. We think that cooperation works best if you physically sit together. And this is what the group looks like. And you see that there's many more people in the group than what I've mentioned thus far. The people that I haven't mentioned yet are the most important ones. Our PhDs, our MDs, our postdocs, they're the ones that do the actual research. And the other people are basically there to guide them and to coach them, and especially in this summer period when everybody is on vacation, to secretly also do some research themselves. Now, what do we do? Let me go through a number of examples. First, 2 very simple examples, because I'm not very familiar with that. This is something that Eugenio Cantatore and Marco Fattori work on. It's called flexible electronics. It's essentially a printing process where you have like an inkjet printer printing on foil, You can print semiconductors and conductors to make interconnects. And you can use that, for example, to make large PIR sensors, to do infrared detection, to do collision sensors, but also to do medical sensors. And in all these cases, it's very comfortable that you can mold the circuit in a large area and make it conform to whatever surface it adheres to. So it doesn't have to be flat. Another example, this is from Peter Harpe. He's worked on very low power electrocardiogram sensors, and he's achieved with that the lowest power dissipation that has been published thus far. But these are areas that are outside of my current own research, and so I don't really know what I'm talking about there. And therefore, for the rest of this, I will focus on RF, because at least that's my own research area, and I can tell a little bit more detail about the projects there. So let me talk about RF then. What are the challenges in that area? Well, we have finite resources in RF, like many people, but in RF, there's an extra one. We have the limitation on energy, like everybody has. But in our case, since it's RF, very often we talk about wireless equipment. And wireless equipment, if it has to be connected to the mains with a power cord, you lose a lot of the benefits of being wireless. So very often these systems run on batteries, and therefore low power and high efficiency becomes even more important. Then there's the spectrum. The spectrum, you can't really lose it. I mean, it's not like you cannot recycle it, but you can overuse it or over-allocate it. And that's what's currently happening in the world. We see that all the frequency spectra and bands are allocated up to 300 gigahertz already in just about any country in the world. It's exactly already allocated who gets to use it for which purpose, and very often not as the only user, but with 2 or 3 other users in the same band. And that means that people experience scarcity. If they want to start a new wireless system, getting frequency allocated to them is very difficult, because we are out of allocation that can be new allocations that can be done. And that means that, at least in the Netherlands, we solve a lot of things with money, right? So people have to go to an auction and bid on spectrum. And nowadays people pay about 100 euros for 1 hertz of bandwidth in a country as tiny as the Netherlands for a period of 5 years. So this gives you an idea how important it is for wireless systems to be also efficient in using this finite resource of allocatable bandwidth. That means we have to go to higher frequencies, because at lower frequencies everything is allocated. We need to go to higher bandwidths because we need to work at higher data rates. We need better bandwidth efficiency to get these higher data rates in a narrower bandwidth, because it saves money. We also need to deal with increasing interference. Remember that I said that we create our own problems? Well, wireless is a really good example. When I was young, and admittedly that was in the Stone Age, in the Netherlands there were probably less than 100 transmitters. We had a few radio stations. We had a few professional users for radio, military, but really not much. Nowadays, most people have more than 100 radios in their home, even if they don't realize it. And with this increasing success, people want more and more radios, use more and more radios. We get more and more interference because these radios share the same radio channel. And so we need to do things to keep them separate, to suppress that interference. And I'll get back to that as well. And then the other thing that people ask more and more is reduce failures and reduce latency. Latency is the time it takes to get a message across from the origin to the destination. And the reason that we're doing that is, or asking for that, is that we're using communication systems, wireless systems, more and more for communication between machines or parts of a machine. And then it becomes much more important that any message gets across very quickly and very reliably. And I'll give some examples of that as well. And finally, especially in the Netherlands, of course, there's money. It needs to be cheap because people need to be able to afford it. And also here, if you manage to make it cheaper, more people will buy these systems and you increase your problems again. And there's again a need for new technologies and new solutions. And that's what makes our job so fun and gives us this job security that I mentioned. But you could ask, why do RF in the first place? I mean, compared to a cable, it's much more expensive. It's much less reliable. It's much less secure. It's much less power efficient. So actually, a cable is a really good alternative. In fact, this video is coming to you not through Wi-Fi, but just through an old-fashioned Ethernet cable, because I want to be sure that all the bits get to you in time and very reliable, and also because I'm Dutch, in a cheap way. But still, we are using RF systems, we're using wireless systems. Why is that? Well, we moved into this house from which I'm now sending this video a few years ago, and when we were moving, we noticed how many cables that we have. This is our utility closet. You see all the cables. This is our attic. See how many cables we brought from our old house. This is what our living room looks like. I'm very happily married already for 38 years, but occasionally my wife explains to me that if I want to remain married, I need to do something. There are some conditions, and one of these conditions is we should get rid of these cables. Cables are all the good things that I mentioned, but they're also inconvenient, they're ugly, they break, they're too short, too long, and once you have everything nicely tidied up, you want to change something, and again you have to reorder all the cables, so it's also very inflexible. There are good reasons to do wireless, to do RF, partly convenience, partly practical, but reality is people want it, and so we need to find solutions for that. So let's look a little bit at energy. This is something already a long time ago we thought about. So more than 10 years ago, we were making these calculations. In those days, there were about 6 billion cell phones in the world. If you would recharge them every day, then you would, even with 100% power efficiency, already spend 1.1 gigawatt just charging cell phones. If you think about the batteries in these things, you would have to do about 1.5 billion battery replacements per year. That adds up to about 45,000 cubic meters of batteries that go to e-waste if you don't find a solution for that. So power efficiency obviously is very important. Also, if you look at the base stations, not just the phones, the base stations are actually worse. 20 gigawatts of power, 2011. If you want to do that with solar panels, you're going to spend 133 million square meters of solar panels just to run the wireless infrastructure in 2011. In the meantime, it has become a lot worse. But it does emphasize the need for being power efficient. And this is for cellular only. There's so many more wireless systems as well. So what do we do? Well, give up on wireless again? That's not going to happen. People want more. There's something called At-Home's law that says people want higher data rates, they want more systems, and so on. And so we need to have different solutions. So in 2011, when we were making these calculations, we said, okay, we need fundamentally different approaches to wireless. How are we going to do that? Well, you could argue that maybe the solution would be to going to higher frequencies, right? Because at higher frequencies, there's less interference, there's more available bandwidth, but the thing people were saying is, now higher frequency you cannot do because you have so much path loss. At higher frequencies, you lose most of your signal. And therefore, it's very power inefficient. You shouldn't do that. Let me show you a few basic things. So you have Shannon's theory, you all know, right? Then there's the Freese path loss equation, you also know. If you combine them, you actually get a very interesting equation that gives you the achievable data rate as a function of bandwidth, transmit power, antenna gains, the wavelength, the distance that you want to bridge, and the bandwidth. And in many ways, it's what you think. Higher data rates you can get with more bandwidth, higher transmit powers, and longer wavelengths, so lower frequencies, shorter distances, and more bandwidth. So this seems to double down on the idea that you should not go to high frequencies. And if you plot this, the nice thing about these type of equations is you can make nice three-dimensional plots. Then you see indeed the thing to do to be power efficient is to go to very large bandwidths at very low frequencies. So it seems like going to high frequencies is not the solution. But that's because we are making an assumption that's not necessarily correct. We are assuming, if you go back to the previous page, oh, sorry, the way. We are assuming that the transmit gain and the receive gain, the GRX and the GTX, which are the gains of the antennas, which are a measure for how much field you generate at a certain distance with a given antenna. And we assume that they remain constant with frequency. Now, if you have omnidirectional antennas, that's a good approximation. Then the gains are by approximation 1. However, you can also make another assumption. You can also say, well, why would we do that? If we don't insist that the antennas are omnidirectional, but if instead we say, for example, that from a certain frequency on, antennas are small enough for all practical purposes, you don't need extendable antennas anymore, you don't need cumbersome large antennas, so we can also keep the antenna size constant, physical size constant. If you do that, then the antenna gain increases with the square of the frequency. And that holds both for the transmit antenna and for the receive antenna. And now the story becomes different. Now your received power actually goes up with frequency, with the square of frequency, in fact. And that means that in terms of energy, you can reduce your transmit power with the square of frequency and still have the same data rate. So high frequency systems can be power efficient. And if you, sorry, if you carry out that calculation, you can see that the curve changes. And now your maximum power efficiency and your maximum data rate is achieved at the highest possible frequency and the highest possible bandwidth. And now we have three things, right? Now we have more room for higher data rates, we have less interference, and we have better power efficiency. So let's go to high frequencies. Yeah, there's this one thing, right? I mentioned shortly that antennas are not omnidirectional anymore if you make them larger than the wavelength. So you need to point them in the right direction. But fortunately, we know how to do that, right? If you get radio telescopes, for example, it's quite simple. You just attach some motors, you turn the antenna in the right direction, and everybody is happy. At least if you want to look at stars and nebula and things like that, because they stay in place. But people, it's a little bit less convenient to do it this way, because people tend to move around. So they're in planes, they're in cars, and so on. So this would not work. But there's other approaches, and the most well-known is the phased array, where you have a number of antennas that are omnidirectional. You combine them with the predefined phase shift, and by changing the phase shift, you can change the direction in which your antenna is transmitting or receiving signals. The one thing that you now need is an adjustable phase shifter, but that should be easy, right? You could, like shown in the red ellipse, you could just make two switches, attach different length transmission lines between them, and you have different phase shifts depending on the position of the switch. So in principle, problem solved. But of course, we're an integrated circuits group, so we want to solve this problem on chip. And we want to do it at high frequencies because that's where you really want to have these phased arrays. Now, we try that. And of course, you know, if the problem is difficult, you get a smart PhD. So in our case, we worked with Yi-Kun Yu, and he designed the first phase shifter. And he tried the same approach, and he ran into a lot of problems. Why is that? Well, these transmission lines you can make. They have losses, okay, but you can build them. But these switches at high frequencies, they start to become really non-ideal switches. When they're closed, they have a lot of losses. When they're open, they have a lot of leakage and parasitics. So they're really not like switches at all if you go to very high frequencies. And that's what Jikun also found. And so after trying for a long time to optimize the switch to be more like an ideal switch, ultimately he came up with a much better solution and said, well, why don't we give up on the concept of switch? The only thing that we want is we want to have a variable phase shift. So if I only say I need a component that has two states, and in these two states, I change the phase in a section of a transmission line by some amount that I want to change it with, like 45 degrees or 22.5 degrees. And then I cascade a number of these segments after each other. Then I can make a digitally controlled phase shifter. And so he worked on that, and he found that a certain type of varicap that can do this function very well. And so he made a phase shifter, and you can see here that over a wide frequency range, it actually does give nice phase shifts and nice steps. They're also fairly equidistant, and you can integrate it into a really small chip, like you can see in the top left. At the bottom, there's the reference to his thesis, so you can read all the tricks and all the results in more detail. But if you look carefully, you see that there is a strange thing going on here. Because these phase shifts, if we want to have a true transmission line, they should not look like this, right? I think many of you, when you took the courses in microwave engineering, people have told you that an ideal transmission line has a phase that is a straight line as function of frequency. These are not straight lines. Now, as long as you make a system in a fairly narrow bandwidth, like Jikun did in the bandwidth from 55 to 65 gigahertz, then it's straight enough. It works. But if you want to make wider band systems, and we do, right, like I just explained, then you need a better solution. So what do you do in that case? Well, first you thank Jikun profusely, you give him his PhD degree, and you go on to the next PhD. And we asked, in this case, Bendy Wang, to come up with a wideband phase shifter that has a much better behavior as function of frequency. And she came up with a concept that's called interpolation, and that allows you to compensate for these inefficiencies in making a perfect ideal transmission line with switches by in a very efficient way. And I'll get back to that in the next slide. But what you can see here in the graph to the right is that the beam pattern for various frequencies is now exactly overlapping. We really can make something that's frequency independent. And the way that Bendy did that was to use interpolation. She said, well, if it's so difficult to get really good segments that you can switch, why don't we make one really good transmission line segments? We can spend a lot of area, we can spend a lot of optimization on there, and then we're going to use interpolation to use a variable part of that one line. And then we also get much better frequency independence. And she did that on the chip that you see at the bottom left. And you can see here that the phase as function of frequency is now much more nice and straight. And at the bottom is the reference to her thesis. So we were quite happy, and we said, okay, this is going the right direction. We can make beamformers, we can make them efficiently, and we can use them across a wide bandwidth. So we thanked Bendy, gave her a PhD degree, and we went on to the next problem, because it's all nice, right? We have now this wide bandwidth, we have the high frequencies, but we started out saying, well, we also need to do low power. And we said, well, we can do low power because we have less loss, so we can lower in the radio path if we use beamforming, if we go to high frequencies. But that's assuming that the beamformer itself doesn't use much power. Yeah, that was a little bit an issue. So the next thing that we did was, after doing some optimizations on the power dissipation of the phase shifter itself, we also decided, well, these radios, most of the time, they're not doing anything, especially the receiver is just waiting for signals to come in. If we could make the receiver switch off and only wake up when something is done, when something is happening, when there's some data to receive, then we could be much more power efficient. So we worked on a circuit that's a wake-up receiver, and essentially what it's doing is it scans the frequency range where there can be signals, and it detects whether there's a signal, but it needs to detect that in a very power efficient way. So we need to make a receiver that detects power at much lower DC power dissipation than a regular radio. And the way we did that is, well, you need to have good sensitivity. So you need to have a lot of gain. Normally that takes a lot of power. And you need a detector. And so you also need usually an LO signal and a mixer and the IF filter and so on. What we did instead was we made an injection locked oscillator, and we tuned that very carefully through the whole band. And we detected when the oscillator would get in lock. And at that moment, we knew that there was a signal present. And you can see the signal at the circuit at the bottom. You recognize on the left the injection locked oscillator. In the middle, there's a mixer that mixes the incoming signal with the oscillator signal. If they're identical in frequency, then we get a DC output signal that gets amplified. The DC amplification is very simple, and you get an indication there's a signal. And on the top right, in the graph, you can see that actually the locking does work. So here you see as a better demonstration of how it works. On the left, what the oscillator output looks like if there's no incoming signal. And so we have an incoming signal here that is not locked, but it's fairly high, -80. Then on the right, you see even if we have weaker signal, but that is locked, suddenly we get a much stronger signal. So this also worked, and Xi did this work. The PhD thesis is again referenced at the bottom, and also she got her PhD degree for this. Good. So now we have a low power solution for very high frequencies and for high bandwidth. That's good, but people want more. I already mentioned this problem of all these batteries. There are so many batteries in the world, and yeah, you want them because having wireless equipment with an extension cable to an outlet is not nice. But for many applications, it's also a bother. It's, of course, the waste. Rechargeable batteries, they wear down after a year or two. Primary cells you discard, which is also not good. But there's also a convenience factor. If we look in our house, we have various sensors, for example, burglar alarms, fire alarms, and so on. And whenever I check, there's always a few that don't work, and they don't work because the batteries are empty. It would be so much nicer if we would not have these really bothersome batteries. And maybe the best example I can give is my personal experience. We have, for example, these 6 fire alarms, smoke alarms in house. And when the battery runs empty, which is about once a year, they start emitting beeps, 1 beep per minute. And that always happens around 3 or 4 o'clock at night. And so I then wake up and I get up and I start walking through the house, trying to figure out which one is going empty. Then usually it's high up on the ceiling, so I need to get a step ladder, need to take the thing down, take the batteries out, replace them, put the thing back on, go back to bed. That happens only 6 times per year. Once every other month. It drives me crazy. It's really not nice. And that's just with smoke alarms. We have so many other things. So batteryless, that would be the ideal, right? What if we could make wireless systems that don't have a battery? Well, we can, at least for some wireless systems. If the power that we need is very low, we could transfer that power in a wireless way. Right? Send the energy that the receiver needs together with the information that we are sending from the base station to the wireless device. So you have a base station, as you see on the top, that has a phased array. It beams data to your sensor, but also just unmodulated power. The sensor converts, as you see at the bottom, the incoming signal to a DC voltage, charges a capacitor, and then also receives the signal and detects when there's the end of the data that the base station sends. And at that moment, it uses the energy that's stored in the capacitor to measure, in this case, the temperature, and send back the temperature through a built-in transmitter. You can make all of this on a single die, including the antenna, including the rectifier, storage capacitor. So this is in some sense the ultimate wireless system. It's really tiny. I'll show pictures later. It's fully autonomous. You don't need to package it. It doesn't need a PCB. It doesn't need external components, and it doesn't need batteries. It keeps working. This is what it looks like at the circuit level. As you can see, it's really simple. On the left, you have the RF input. Then you have the RF DC converter, which is a resonant version of the traditional rectifier, multi-stage rectifier. That also does voltage multiplication. The end of burst monitor detects when there's no further signal coming in. Then it waits for a certain time. That's the CS that you see there in the end of burst monitor. When that gets discharged, then it enables the temperature correlated transmitter. That's a really nice way of saying that we were lazy. Good engineers are often lazy. At least that's what I keep telling myself. So we made a transmitter where we did not optimize the transmitter for temperature stability. And so what happens is that depending on the temperature, the transmitter transmits at a different frequency. And so we don't need any circuit that encodes the temperature in a digital way on the transmitter. We just look at the received signal in the base station. We determine its frequency. And from that, we know what the temperature was. So a really simple circuit. But when you measure it, it actually works. On the top left, you see how much DC power we can get from the incoming signal and the related efficiency that you get if you calculate that. And you see that the efficiency is, of course, a function of the load current, so you need to optimize that like any system. And then at the bottom, you see that we do indeed get a signal back from the system after it measures the temperature. And then the frequency of that signal, as you can see here, really nicely correlates with the temperature. So the system actually works. And the nice thing is, if you've worked on this for a number of years, or in this case, the PhD student worked on this for a number of years, and you looked at this on your monitor and cadence, and you look at all the layers and so on, you don't realize anymore how tiny this is. The whole circuit, you can see in the top left corner, is about 2 by 1 millimeter. Most of it is actually the storage capacitor, because you need to store nanojoules of energy to make this work. There's a very small transmitter, the center top, and the rectifier is close to the antenna. The antenna is the single bar in the middle on the right side. That is just a monopole antenna that is using the capacitor, the storage capacitor, as its ground plane. And in that way, we managed to get everything on one chip. The antenna looks like it's wasteful. There's a lot of empty space around it, but yeah, that's what you need to do to get a working antenna, unfortunately. To show you how small it is. This is really how tiny the circuit is. It fits on the tip of your finger, and then you need to be very careful that you don't lose it. So you can produce this in high volumes and at extremely low cost. The work in this case was done by Hao Gao. His thesis is at the bottom again, and also he, of course, got his PhD degree for this work. After we had done this, we found that, well, I'm going to skip the next movie. We found that there's some potential other uses for this that we had not even realized. For example, there was a company in our neighborhood that makes enclosures, housings for chickens, for farmers that hold chickens. And apparently, we were not even aware of that. There's a problem keeping track of chickens. You want to know where they are at any moment in time. because if you find an egg, then chicken farmers would like to know which chicken has laid that egg. But nowadays, a chicken farm, you have, I don't know, 100,000 chickens or so. And keeping track of that manually is out of the question. So you need to automate that. And you need to do that in a chicken barn with, like I said, maybe 100,000 chickens, where the barn is maybe 50 or 100 meters long. And you need to do that with an accuracy of about half a chicken. We had a student actually do experiments where we had a surrogate chicken in the form of a small robot that had one of these temperature sensors on. And then we had the thing that you see in the middle. That's a very accurate pen tilt mechanism that can, at a fraction of a degree accuracy, move these two horn antennas. And then by moving the horn antenna such that you get the maximum signal just to the left and the right, and then you turn it until, if you subtract the antennas, you get the exact zero. You can achieve the required accuracy. Of course, only if the chicken sits still. So that's not quite good enough. We're still working on that. But it shows the kind of things you can do. Another study that another student did shows that you could also use this to make in a stadium during a concert, give people a flashlight, and you can then program the color of the flashlight wirelessly and the intensity if you know exactly where the flashlight is. If you would have one of these sensors in every flashlight, then you could find the position very accurately, and you could make a virtual display consisting of many, many pixels, and you could have even moving pixels displayed just from the collection of flashlights that all the people in the concert hold. So there's many applications, and that we see that a lot. Whenever we find a solution, then we create a problem, a demand for yet another application. In this case, the temperature is not even important. It's the location that's much more relevant. So yeah, all good news thus far. We've solved the energy consumption, the efficiency, we have increased frequency, we have increased bandwidth. Everybody should be happy. But again, we create our own problems because of the success of our wireless systems. Because everybody now is having wireless systems, and many of them, right? I mean, when you just look at what you carry with you, how many wireless devices you have, then you start to realize that even with all this extra bandwidth, we are still creating interference. And so we need to get rid of this interference somehow. So how do you do that? Well, again, you get a good PhD student. And in this case, it's quite interesting. We got a PhD student that was not specialized in electronics. It was actually somebody that specialized in signal processing. And he looked at these problems in a very different way. He said, well, you don't have a phased array, you have a MIMO system. Well, for us, that's the same thing. And then he said, well, in the MIMO system, you need to decorrelate the signals to reconstruct the individual transmitters. But in a regular system, you do that in the digital domain, in the DSP, and that's way too late. Because then with all these interferers, you need to spend all this power to very linearly and accurately transform the antenna signals into digital data. So he said, that's not smart, right? You should follow the principle of what we do in signal processing. You should do this transformation, this decorrelation, as early as possible, close to the antenna. And what he proposed was, well, you should do an complex matrix multiplication of the antenna signals to get the same number of antenna signals, but with different signals, in such a way that you maintain or optimize the decorrelation between the signals and simultaneously minimize the dynamic range of each of the signals, because then further processing requires the lowest amount of power. Power dissipation is directly related to the dynamic range of your signals. So what he proposed was very simple. On the left side, you have a number of channels coming in on these antennas that are the sum of a number of transmitters. You add some noise to it, and then you have this matrix multiplication. And then you go to the rest of your receiver and everything is happy. The only thing but he can be forgiven because he is not an electronics guy. He did not realize that now you need to make an analog circuit that does complex matrix multiplication at RF. So the trick was that we didn't tell him that this was difficult. So he just did it, and he designed the circuit that you see on the right. He actually designed an IC for that, and it actually works. So this circuit that you see on the left, the chip, takes 4 antenna signals, then does this matrix multiplication. He also developed the algorithms and the digital control for it. And on the right, you can see that, for example, the situation with the red interferer coming from the direction indicated in the diagram on the top right is compensated for by equivalent antenna diagrams like shown in blue. And then the signal that you get from these antennas that you see in the power spectrum in the graph goes from the red curve with the strong interferer and the very weak wanted signal, gets transformed into something with much smaller dynamic range, but still the same information content. Again, the thesis of this is referenced at the bottom, and Johan van de Heuvel, he did this work. He, of course, did get his PhD degree as well, and we are still working together with him. He's now at a different company, and this also holds with many of our other PhDs. We continue the cooperation with them. Yet another idea, a little bit inspired by the work of Johan. When you think about what we're doing, we have these interferers, and we want to distinguish the interferer from your wanted signal. You can do that in frequency. That's what people traditionally do. Right? You have filters at the antenna, filters at IF, and these filters, they are selective in the frequency domain. But with the spectrum getting more and more crowded, interferers get closer and closer in frequency to your wanted signal. So separating in frequency is getting increasingly difficult. So that's where we, as a next step, what you saw with the work of Johan, we said, well, then we're going to try and use not the frequency, but the direction, right? The spatial information, because we have a phased array anyway. And that works, but it's still not enough. So we thought, well, what's the one distinguishing feature between an interferer and our wanted signal? Something that we will always be able to count on, that's not going to disappear in the future, even when there's more and more systems. And then we said, well, one thing you can always rely on is Murphy's law, right? That's more basic than any laws of physics. Murphy is always out to get you. And what does Murphy say? Well, he says your interference signal is always way stronger than your wanted signal. So why don't we make a filter in the amplitude domain that passes weak signals and suppresses strong signals? I admit, crazy idea, but what if you could do it? Well, it would, on one hand, solve this problem, right? Even if signals are very close in frequency, even if they're coming from just about the same direction, you still could separate them. But Murphy being Murphy, probably when you would implement a circuit like that, the situation would reverse and your wanted signal would become larger than your interferer. But actually that's not the problem, is it? Because then we just receive the wanted signal and we forget about the interferer. We don't need to reconstruct the interferer. So this really is nice. So looks like a good idea, but difficult and crazy. So we got another PhD, in this case Erwin Janssen, and we told him, okay, what we want to do is we want to have a filter that is selective in the amplitude domain. And the way we thought about it was, well, we need to do some non-linearity, right? Because that's the only way to make amplitude selectivity. Because if there was a linear circuit, there would never be amplitude selectivity. Then there would always be linearity, superposition, and so on. So it has to be non-linear. And so we told Erwin, please, as a first assignment, figure out how to make a non-linearity that allows us to suppress interferers stronger than the wanted signal, but in such a way that we can always reconstruct later the complete signal. Right? So it has to be a function, a nonlinear function that can be inverted. And this is actually one of these things that I always like telling about, because it shows you how things go and why we enjoy working with PhD so much. So Erwin went to work, he came back a week later and said, yeah, I have the optimum function. Oh, great. So what's the optimum function? Well, it's a polynomial with a degree of 3. I said, no, that cannot be, because we know that these cannot be inverted. So go back, do your work again, come back next week with the right answer. So he went back, came back next week, and he said, yeah, I've thought about it, but I was right after all. And so first I thought about it a little bit, then I discussed it with him a little bit. He was in fact right, because we don't need to reconstruct the input signal, at least not all of it. It's quite okay if we cannot reconstruct the interferer, because we are not interested in that. As long as we can reconstruct the wanted signal, it's quite okay if we cannot reconstruct all of the signal. And if you use that condition, then you find that a third order function is in fact the best thing you can do. So the diagram on the right shows how that works. You have a circuit that's called NIS, nonlinear interference suppressor, that takes an input signal that you see on the vertical axis, a sine wave, goes through an NAS transfer, a third order function, gets distorted in an output signal that's at a very different frequency. Then as long as you make that transfer function exactly right, and that's something I'll come back to on the next page, then you can make sure that none of the interference signal ends up at the output frequency of the interferer. Now you can wonder how that works. This page explains that. You can see that you can build your signal from multiple components. You can just have gain. That's the first set of graphs at the top. But you can also have saturation, which is the second. You can have a third order power function, which is the third. Then the nice thing about this third one is that you don't have superposition. And so if you make your circuit such, if you dimension your circuit such that it suppresses your interferer, it doesn't suppress your wanted signal. So you also build a circuit for that. It's surprisingly simple. As you can see here, it consists of two signal paths. You have a signal path at the outside, the two transistors at the bottom that are essentially common as switched as diodes, and then feeding into common gate transistors at the top. And then in the middle, you have a regular differential pair, and the output of the differential pair and the common gate transistors are tied together, they're added. And if you do it that way, you have a signal that goes through the common gate that is not inverted, and a signal that goes to the differential pair that is inverted. And for one amplitude and one amplitude only, they cancel each other. The amplitude at which this happens, you can set by changing the current through the differential pair. And what you have created then is the equivalent of a notch filter, but a notch filter in the amplitude domain. So at the bottom right, you see for a number of currents through the differential pair that there is one amplitude that gets suppressed. That's the notch, and you can shift this notch just by tuning that current. And at the top, you see the tiny circuit that does this actually. Erwin even made the circuit in reality, and I can show, hopefully, let me see. I can show that it actually works. So what you will see in this video is a test setup with this IC, in which we show that it works in reality and also the problems that you encounter. So the lab setup that Erwin built has this IC, a vector signal generator that is the transmitter. You have a software-defined radio for the rest of the receiver, and everything is controlled from LabVIEW, as you can see here on the right. So we input two signals, an interference signal at 1.9 gigahertz and one signal at 1.93. That could be even closer, but then it's not so easy to see. And you can see that the interferer in this case is 50 dBs larger. Now, if you just switch on the NIS, but you don't set it to the right amplitude, so the notch is not at the interferer, it's also not at the wanted signal, you just get a mess out of it, right? Because some parts of the signal are attenuated, others are not. So that doesn't really help. You really need to set the notch at the right amplitude. And that's what he shows in the next part of the video. So here you now see, I have to wait for one more second. You see that if you switch this on, then suddenly your interferer goes down and your wanted signal goes up, and you gain about 30 dBs in signal to interference ratio. Now this is really nice, but if your environment changes, like it usually does, people walk around, they touch things, they even touch antennas, suddenly your interferer and wanted signal are at different amplitudes. And he's going to show that by bringing his hand close. And you see that suddenly the interferer goes up again because it moves in amplitude away from the notch. So nice idea, but not quite practical yet. And it needs something additional. So he also developed an adaptive control algorithm that moves the notch to track the amplitude of the interferer. And in the last part of the video, you can see that this actually works. So now if he switches this on, he still has 30 dBs of interference. Even if he moves his hand close, you can see that it never gets above the minus 30 dBs. So this gives you an idea of what you can do with nonlinear interference suppression. And again, you might think, this is great. Now we've solved this last problem of the interference. Now the world is good. So Erwin got his PhD degree. The reference is again at the bottom. But it's not perfect. Because one thing we forgot to really keep an eye on, and that's the power. Sorry, apologies. I should have stopped the video because now it's playing ads. My apologies for that. Okay, so the problem we had is that the NIS circuit itself is actually very power inefficient, because what we do is we have two amplifiers that both need to accurately amplify both the interferer and the wanted signal. And to do that, they need to have a large dynamic range and they need to have a lot of power. So in the end, the system worked. It worked quite well, but the power dissipation advantage was not what we expected. So again, we asked another smart PhD student, in this case Guangyang Yang, and he came up with a new circuit where the combination of the signals is done right at the input rather than first amplifying it. And you can see we can now again make these notches. We can again move them together with the biasing of the circuits, which we now do with the common mode signal at the PMOS transistor at the top and the NMOS transistor at the bottom. The system itself looks a little bit complicated, but when you look at it, it's basically a current folded double balanced mixer. You have the RF signals coming in from both sides. Then you have the transistors on the outside. They are actually acting as a common gate. Then they get current mirrors with current mirrors at the top and bottom, and then go into what's essentially a differential pair in both halves. And that works like a double balanced mixer. And with that, we can actually achieve the same thing, but now at a much lower power level. And we can show that the power level is not related anymore to the dynamic range requirements of the interferer. So Guangyang also got a PhD for that. And now we basically have, as you can see in this graph, a system that can work at very high frequencies, that can work with very large bandwidths, that can deal with all kinds of interferers, and that can be really, really low power. Now we thought we were ready, but of course not, right? Because what happens now is that people start thinking, oh, if we can do that, we can do more. And one of the questions we got was from company that makes shock absorbers for cars. And they said, well, we really would like to have shock absorbers that can wirelessly communicate to each other, because we want to make them adaptive, and we want them to agree on what setting they are on, so that they can together make sure that you have a very comfortable ride. But even more importantly, when you have an emergency, like you need to make an emergency stop, we want all shock absorbers to work in unison to go to this very rigid mode where you get maximum braking power. If you don't do that, you can have accidents, and if 3 of the 4 shock absorbers do that and the 4th one doesn't, then you have a really big problem. So essentially they said, we want all of the things that you already have, but now it needs to be just 2 more things. It needs to be extremely reliable, needs to always work, and it cannot be slow, because if it takes too long to get a message across, then there's no point anymore, right? Then you already have a crash. So again, we got a really good PhD student, Carlos Mendes da Costa Jr. We explained the situation to him, and we already had done some projects in this area, because like I said, more and more people start using wireless for situations where you have machine-to-machine communication, and where you really need to have this combination of high reliability and low latency. So he looked at this and said, well, essentially this is something that we can deal with like any wireless system. So we again going to do the wake up, and we're again going to do the diversity, multiple antennas, all these things. But we have now a multi-dimensional optimization. And for that, he used Pareto front optimization and in his algorithm. And now we can jointly optimize latency and reliability and power dissipation, because the other thing is that these things get their power from energy that's generated within the shock absorber itself. He designed a circuit for that. You see that at the top left. Essentially, it consists of the same things we have discussed before. So the beamformer, the interpolation type of beamformer, the signal combination, the interference suppression, all these things. But now the thing was to optimize it with an algorithm, to control it with an algorithm in such a way that you jointly get all these things that we want: low latency, high reliability, and the energy efficiency. And of course, like with many of our projects, it does not end with a cadence simulation. So in this case, we went as far as actually building it into a car, like you can see in the top right. And of course, somebody had to drive that car, and that honor befell to Carlos, because who better to do this? What better motivation can there be for an IC designer than to drive a car in which his own designed IC is responsible for the safety? So you see some of the roads that he did the test on, and you can see that, in fact, he can get the kind of reliability that in this case was required, which was very high, but it can be worse. So this works quite well, but we are now doing a project basically doing something very similar for airplanes, and there the reliability requirements are even higher, and I cannot tell much about that at this moment because the project is still ongoing. But here we need to think about failure rates that are essentially really zero and latencies that are really extreme. So again, we are working with airplane companies. We actually do measurements in airplanes. We're trying to build demonstration systems that can be used in airplanes, and turns out we have to do even more than we need to do for the car, because an airplane is really a very unfriendly propagation environment. But for that, you have to wait until the end of that project. We again have a very smart student, so I have good hopes we also come to good solutions there. But at this moment, I cannot tell yet if there is a solution or what the solution is. The IC is actually today being measured in our lab. So hopefully, I was hoping I could tell you already something, but we had a small, tiny problem with the PCB. Otherwise, I could have told a little bit more. Then a very different thing, just to give you an idea that we also do things besides wireless systems. Because well, we think we have solved all the major problems there now, but we know from experience that we are going to generate new problems in the future. Something very different is a problem that we got again from industry. It started with the idea that people historically want to explore things, right? And also in industry that's true, or in the world in general. We want to know what's going on in pipes. We want to know what's going on in a nuclear reactor. We even want to know what's going on inside people. And therefore, it would be so nice if we could have a technology that allows us to go inside and find out what's going on there. You can do that in many ways. You can do that in non-invasive ways with modeling, with imaging, with spectroscopy. And that's done a lot, but it's still indirect. Or you can actually go invasive, put some sensors or sensor swarms in this environment, and then you can do things that we still cannot do with non-invasive methods. For example, if you have pipes and they're fully metal and they're thick metal, then many of the imaging and non-invasive techniques don't work. So the question here was, can you do pipeline inspection with essentially sensors going inside the pipe? And you can go two ways. You can make a very perfect sensor that can do everything. But the problem is that these things get big because they need to have large batteries. Or you can make a swarm of very small sensors that can be small, that can be low weight, that can do very little individually, but together they can solve the problem. So that's what we did in this project. We made very simple sensors, but then we had the problem, how do you optimize them? Because a small sensor has very limited energy, so you cannot just do overkill on everything. You cannot do too many samples, you cannot store too much data, you cannot have too much dynamic range. But you don't know what's required because you don't know what's going on inside this pipe. To know that, you would have to be inside the pipe, but then your sensor doesn't work. So this is a chicken and egg type of problem, and we decided to find all these parameters that we needed to set in a different way. You cannot do that in a truly top-down design fashion. So what we did instead was, well, we said, let's do it iteratively. We try something, we make the best design we can imagine. We try something, we find out what's going wrong. And then we're going to make a simulation model. And in that simulation model, we are going to evolve better sensors with artificial evolution. And you do that in a number of iterations. You build this virtual world. You evolve better sensors for the virtual world. You replace these sensors with physical sensors according to design that was done in the virtual world. Put them through the real world again. Improve the model that you have of the virtual world, of what you think is going on there. Again, you evolve better sensors. You do that over and over again. And in the end, you get sort of a dual loop optimization that very efficiently allows you iteratively to come to better sensors. Of course, also this you cannot do just in theory. So we needed to experiment with that. Again, we got a lot of students. You can see that we have a setup there that includes a swimming pool and some pipes and some water basins. And of course, we need students to retrieve the balls from the reservoirs and so on. Very different type of project, but yeah, it actually does work. To do this, there's a lot in there. I need to go through here much more quickly than I wanted to. I could talk about this project alone for more than an hour. We had a really large team. We developed the software, the user interface, the electronics, everything, and the test setups. It is currently being piloted for commercial exploitation. And we're doing that together with, of course, another company. But also here, it's still a lot of fun. You can see here some of our students doing these experiments. And yeah, students and playing with water. It's always a good combination. They flooded the building only twice, but I had to promise our director not to do it the third time. Still, it shows that with electronics, like I started out saying, there's a lot of fun to be had. It's a great area to work in. And I hope that you also have that feeling now that this is something that is really worth doing as a career. I can definitely recommend it. I've been in this field now for close to 40 years and still have not had a single boring day. That brings me to the end of this presentation. Thank you very much for your attention. And please, feel free to ask questions.
Yes, Professor, thank you very much. It was quite an insightful talk we witnessed. And yeah, there are definitely quite many questions for you. And first I'll be reading them out, and then I'll request the audience members, if you have any questions in mind that you would like to directly ask Professor, then you can raise your hand and we'll unmute you and then you can talk to him. So yeah, the first questions is how development of sensors contribute to analog circuit in modern days?
So how the development of sensors? You mean the work that Peter Harpe is doing, for example, or what was the question?
The question was, I guess, how development of sensors contribute to analog circuit in modern days. I guess it's a very open-ended question, so you can answer.
Okay. Yeah, so I think if it was the first question, it probably was referring to the temperature sensor then. I think the thing that we saw there is that if you think about analog circuit design, that if you really go to the extremes, right, you can only transfer a very small amount of energy into a small sensor because there's just not room for a large capacitor or a large battery. And that means that you need to go to the extreme of power efficiencies. So we can store at most 100 nanojoule on this chip. Right? That means that you need to do everything, the temperature sensing, the receiver, the transmitter, everything with this 100 nanojoule. And the only way to actually do that is with a fully analog circuit. If you really want to go to this extreme, you cannot have a microprocessor and software. Digital is great. Software is really nice. I still do some of that myself as a hobby, but it's not efficient in terms of power. If you really want to go to extremes of power, then you need to minimize the functionality, the number of transistors, the number of wires, everything to the bare minimum. And that drives you into the direction of analog circuit design, but that also drives analog circuit design because you really, like I explained in this cube, you really go to the limits of what's possible. Is that answering the question?
Yes, I guess that's quite a comprehensive answer. So, Souvik Chatterjee, if you still have any follow-up questions, then do let us know through the chat or through raising your hand. So, moving on, the next question is how the sensed temperature will be transformed to RF level in batteryless temperature sensor?
To RF level?
Yeah.
Well, essentially what we're doing is we have, if you look at the slides later, there's VCO in there that is actually not voltage controlled. It's actually a free running oscillator. And that's running directly at 60 gigahertz. Again, we have to be really minimalistic. So no IF, no mixers, no LO, no PA. There's no energy for that. Right? The only thing that we can do is we can run an oscillator directly at the transmit frequency. We make the oscillator temperature dependent. That's actually quite easy. We felt that if we didn't do any effort, it's already temperature dependent. So the temperature is already encoded in the frequency. And we couple that with a passive coupling network to the antenna. And that's all there is, again, because you don't have energy for anything else.
Okay, and a follow-up question by the same person is it possible in future to have mobiles without battery, as they are one of the major contributors for e-waste?
That depends on how you define mobiles. So can you have wireless devices for simple communication without batteries? I think that's possible. If you think about a mobile like something like this, you know, with a large screen and a fast processor and 5 cameras and things like that, forget it. It's not fundamentally impossible. Wireless energy transfer is easy. Right? You can just transmit, you can scale things up. Now we are transmitting nanojoules, but we can easily transfer megajoules. The only problem is people don't like it. Right? Because if you get in the way of such an energy beam, then you get this crisp skin, right? It's like chicken out of the oven. It's not something that people enjoy. Eventually you become very ill and you die, and that's not recommended because, well, it's not healthy, right? So I think really there's a limit to how much energy you would want to transfer wirelessly, just out of safety reasons. So I think that I can't see how we could do the power that you need to run large displays, cameras, speakers, microphones, all these things, not just the radio. The radio part is actually relatively simple in some sense, but especially things that need to do something like generate light or generate sound, things that you cannot reduce in power without losing brightness of the display or losing volume of the sound. Those things, they need power, and those levels of power at this moment look like they would be rather unhealthy.
Yes, sir. And next question is by myself. So do the signals sent to such batteryless sensors need to be modified in any way at the transmitter end? Or can it work with any signal?
No, in principle it works with any signal. There are a few requirements. It needs to be pointed exactly in the right direction. These sensors are really small. You need a lot of antenna gain, and it needs to be long enough. The transmit signal needs to be long enough to fully charge the storage capacitor, but it also needs to stop, because the sensor only starts transmitting when the signal that comes in stops. Otherwise, you would never be able to detect a weak signal coming from the sensor. Right? So it has to have some properties, but it's very limited. You don't need much.
Okay, and how, like, if you could please illustrate, are these batteryless sensors different from the RFID tags that we are used to seeing in our travel cards or our?
Yeah, there's two big differences. One is that this can be really small, right? The cards that we have for traveling or for entering our building or things like that, they actually have a very tiny chip with a large antenna. They typically work at 13.56 megahertz, which means that you need a large size antenna to pick up enough energy. And therefore you cannot miniaturize this much further than the size of a card. Well, maybe a key or a coin or something like that, but not really tiny. And therefore you can also not fully integrate it on a chip. So that's one thing. The other thing is that this is near field coupling, which means that it only works at relatively short distances. So it works at a few centimeters, but this sensor that I showed, if you have a sufficiently high gain antenna and you still stay within the limits of the regulations, then you can go up to 5 meters.
Okay, that's some interesting advances, definitely. So the next question is about the amplitude domain filtering. So it is, isn't amplitude domain filtering just entrainment?
It's just what? Just
entrainment. I guess that's not a word I'm familiar with, but that's what the audience member has mentioned. So Udit, if you can please expand on your question or clarify it in some other way.
So the question was for the person who asked the question, right?
Yeah. So Udit, if you can please rephrase it in our, so it's he's saying injection locking.
Injection locking. No, so the NAS, the interference suppressor that we do with the nonlinear circuit, there's actually no oscillator in there. It's really it's more like an amplifier that has strong distortion, right? A very bad IP3, or I mean, it's not even one to be compression. It really falls back again, and I think maybe that's the most important property. A normal amplifier, if you increase the input power, then the output power initially goes up proportionally, but then at some point saturates. This one goes beyond saturation and starts decreasing again with increasing input power. And that allows you to have some amplitudes being converted to a zero power output signal. And that is something that you cannot do with regular saturating amplifiers, but it is not involving an oscillator. The injection load oscillator was for the wake-up receiver.
Okay, sir. So the next question is, in interference suppression, how the knowledge is obtained between signal and which is interference, and is it based on power level only?
Yeah, no, that it depends on the application. So we started out, the project of Erwin started out with the problem that you are your own worst enemy in a sense, right? When you think again about phones like this, right? There's 4 types of Wi-Fi in here. There's Bluetooth in here. There's near field in here. There's I don't know how many bands, 2G, 3G, 4G, 5G in there. And in a very real way, that phone is its own worst interferer because that's very close by. But the good thing is that you know everything about the interference signal, right? Because you're generating it yourself. And there that was what Erwin started with. We use that knowledge to very accurately position the notch of the NIS, because we know what the interferer is, except if people come with their hands close to the antennas. And then you saw the adaptation that I showed in the movie, that you can compensate for that. Now, Guangyang, there we said, well, nice, but not good enough, right? Because there are also problems where the interferer is not in your own device. And so he looks at the combination of parameters of the interferer to determine what the interferer is. Frequency, angle of arrival, modulation properties, things like that. And said, okay, this is a signal I don't know, I'm not interested in. So that I'm going to track the amplitude of and then suppress it. But then, of course, the amplitude is only an approximation because you cannot separate the interferer yet from your wanted signal. So it's, in some sense, again, this chicken and egg problem, but again, one that you can solve iteratively. So again, with an adaptive algorithm, you can do better and better. And so at the moment the interferer comes up, initially you still have some interference, but then when the algorithm kicks in and iteratively optimizes the notch, to make sure that you get a perfect wanted signal. And you can do that, for example, looking at the EVM of your wanted signal. Right? That's a very simple check. If you optimize for that, then you automatically put the notch in the best position. And yeah, then it's a matter of how quickly you can adapt this notch filter. But yeah, you need some information about what your interference is, and that means you need to have some indication, some parameters that allow you to say this is an interferer. And if that's not possible, you can still use knowledge about your wanted signal, because usually from your wanted signal, you know the frequency, you know the type of modulation, you know a lot of things. And if you say, okay, this is what I expect, the signal should come in on one of these constellation points, for example. And if it's not, I keep tweaking the notch until they get as close as possible to the constellation points. And then, even without knowing anything about the interferer, it's the best I can do.
Yes, I hope that answers your question. And next up, we'll have the question from Mitu Boral. So I have allowed the microphone for you, so please unmute yourself and go ahead with your question.
Good morning, sir.
Good morning.
Sir, I'm Audi, sir, from NIST Gorakhpur. Sir, actually, my question is that whatever the design you are doing, sir, can you please tell what type of tools or softwares you are using and how you are fabricating this type of things, where you are fabricating, or that means how much money it is expedited, and also whether after this fabrication also the practical circuit, the practical IC is working or not, or what type of analysis you are doing, how you are analyzing the result. Can you please explain, sir? Because you are practically you are doing all the things. I want to know this.
Yeah, sure. So the question was about the tools and how we use them, and yeah, also the investments that are required for that. Did I understand it correctly? So yeah, sorry.
Hello, sir. Yes, sir. Yes.
Okay. So we use, sorry.
Tools, and after doing the fabrication, how you are testing or how you are characterizing?
Okay, very good. Yes, testing and characterization. Yes. So in general, yeah, I regularly have discussions with our managing director, and she always asks the question why we are not as smart as our colleagues in signal processing who are quite happy with the PC and MATLAB, while we insist on very expensive tools, software tools for design, and then we insist on making ICs, which is very expensive, and then to make things worse, we also want to measure them with very expensive equipment. So in general, I think the answer is, yeah, we use mostly rather professional and expensive tools for everything. So most of our design is done with Cadence. Personally, and many of my colleagues also have a simple simulator and MATLAB on the side to do some simple modeling. But the actual, let's say the real design work is done in Cadence. The good thing is that we do get a discount as an educational institute. Otherwise, I could not afford that at all. Then we also use occasionally ADS, Momentum for modeling EM structures, CST. Then we go for fabrication. Usually we go through Europractice, which is an organization in Europe that collects designs from many universities. And then we share a common mask. Right, so that brings the cost down, so we typically pay probably 10% or so what you would pay for a commercial MPW location. So that's that also helps. Then we through Europractice we typically process in TSMC. Nowadays a lot in 28, 22 nanometers. We are currently talking about going to 16 and 7 nanometers. It's an expensive hobby again. It takes a lot of money, and yeah, there's always this trade-off between how much risk do you want to take, how many iterations of silicon can you afford, and that is one of these more difficult things. And of course, we do lots of design reviews to minimize that risk. And then, yeah, the worst thing for us is the measurements. We pay commercial prices for measurement equipment. We use network analyzers with frequency extenders. So PNAX frequency extenders up to 500 gigahertz. We have spectrum analyzers in the same frequency range. Oscilloscopes that go up to 200 gigasamples, 2-channel probe stations that allow us to probe in the terahertz range. The last 2 years we invested 3 million in measurement equipment, and that's about 1 year's turnover of the total group. I mean, this is really an expensive hobby, but we need to do it. In this field, just having a simulation is not going to convince anybody. And even having measured silicon is usually not enough. We really need to make the extra step, build it into a car, put it on a surrogate chicken, make it into an airplane. All these things you need to do to convince people that you actually solve the problem. We very much like working with industries, but that's what it takes to convince them. And being from industry ourselves, mostly, we also have this need to convince ourselves that it's not just a circuit that we verified, but that it's actually a solution for an application that we validated. So yeah, expensive hobby, and for that, there's no alternative to using commercial tools yet. We are experimenting, and that's a slide I did not show, but maybe we are experimenting with open source tools for circuit design, and also with open source fabrication through eFabless. So we are using the same tool chain as Skywater, but now for analog circuits, and we are going to do a run with Skywater, in which we are going to sponsor up to 100 people, anybody who is interested to join us to use these tools, and we will pay for the processing. So if you're motivated by this talk or by anything else to design your own chip, then please let us know, and we will see whether we can fit you in on this run.
Thank you so much, sir. Thank you so much.
Thank you very much. And now we'll be moving ahead with the rest of the questions. There are quite a few, many remaining still. So I hope Professor has no problem with staying with us for some time more.
No problem.
To the others who might be in a hurry because we have already passed our scheduled time. So we have already supplied the feedback form links in the chat box. So you can log into any of those, and after filling out those, you can get your certificate of participation. Thank you very much for joining, and now we move ahead with the rest of the questions. So the next question is LNA still around in RX architecture at millimeter wave? If yes, how much practical gain in dB we achieve at millimeter wave?
Yeah, they are still around, basically because if you don't make gain at LNA before the mixer, then your mixer adds so much noise that you would have to increase your transmit power a lot. And that has two disadvantages. Usually that takes more power than the LNA. And also it's not always legal, right? There's limits to how much you're allowed to transmit. So many systems still have LNAs. You see the mixer first architecture becoming increasingly popular at lower frequencies for lower performance. So microwave region, but at millimeter wave and up, we still use LNAs. The exception being if we go to circuits that work beyond Fmax, because there we don't have a choice, right? You cannot make gain anymore. Typical gains, yeah, as a rule of thumb, I would say you get roughly, if you have a multi-stage LNA, we typically go for things like 10 dBs, 15 dBs of gain, multi-stage. Yeah, the gain you can get for a transistor is never more than Fmax divided by your center frequency. Right? So if modern CMOS technology has an Fmax around 300 and you design something at 150, then you can be quite happy to have any gain at all. Right? It's never going to be 3 dBs up from a single transistor. So that's why you need to go to multi-stage. And that's why you cannot do that beyond Fmax anymore. But yeah, it is in many cases at the system level still a good trade-off to have an LNA.
Okay, thank you, sir. And the next question is, didn't you face any issues with respect to wire bonding at 60 gigahertz frequency while designing ICs?
Oh,
How
yeah.
did you, yeah, there is a follow-up question as well. How did you model them accurately while designing the LNAs at these frequencies?
Yeah, that is a big pain. Yeah, bond wires are something we really do not like at these frequencies, but you have to live with. So what do? We bought our own wire bonding machine, so we can make the wire bonds as optimal as possible. We make PCBs with cavities so that the surface of the chip is flush with the surface of the PCB, and then you can do ribbon bonds across this small gap between the start of the cavity and the start of the bond pad on the die. All these things help. It still is a bother. We've just recently, part of the 3 million that I mentioned, we invested in a flip chip machine, because if you go even higher, it becomes more and more impossible to make high performance circuits. And with bond wires, it's not just the impedance it adds, right? That requires you to adapt your matching and then make circuits more narrowband. Also the uncertainty that you have. So you have not as much gain as you wanted to. Right? And are you now going to blame the bond wire or to blame your chip? Or somebody else, right? Measurement equipment or so. And then there's things that you cannot even solve with compensations, like, for example, if you have magnetic coupling between bond wires, if you have a high gain amplifier. One of the projects I did not mention, we designed a wideband amplifier from 20 to 40 gigahertz with 50 dBs of gain. If you do that the regular way with bond wires, you make an oscillator. Right? Because you never get 50 dBs of isolation between bond wires. So bond wires are universally hated. It's just not so easy to get around them. So what we do is usually a multi-step approach. We usually make a PCB where we bond wire all the low frequency stuff. But initially we put the PCB then on the probe station again, and we measure with probes at the bond pads in a calibrated way the performance of the silicon by itself. least then there's no uncertainty for that. Then we bond the high frequency signals and we measure the PCB, and then we know what the PCB does and what the bond wires do. And the PCB we can usually de-embed separately. So at least we understand what's happening where. But I think flip chip is in many cases a much nicer solution. And there is in the future, and there's a number of things that look hopeful. One of the things is that we are experimenting, and in fact there's going to be a PhD really soon now, Piyush Kaul, one of our colleagues that you saw in the introduction of the group. He did a PhD where he actually designed an IC that sits in a waveguide as a package. And that has the low frequency signals bonded out, but it has launchers for the waveguide at the input and the output. And that way you get rid of the high frequency signals. In a similar way with temperature sensor, there we have the antenna on the chip. I think we will more and more go to not even trying to get high frequency signals on and off the chip again, because, you know, at least not with bond wires or with bumps or anything.
Yes, sir. Thank you. And a follow-up question is, how much gain variation have you observed at millimeter wave frequency when you design LNA or PA in the schematic versus layout versus tape-out chip measurement?
Yeah, really good question. Yeah, that's one of the reasons why we insist on making silicon. So if you go from schematic to layout, it depends a lot on the specific design and especially the experience of the designer. We work a lot. You've seen most of the work is done by PhDs. They have very little experience, and so typically we see 3, 4, 5, 6 dBs difference between schematic and extracted layout, even with help and coaching from experienced people. But that can be optimized, and you can then, with better modeling and better optimization, you can get it back to 3 dBs in a frequency range, let's say 50 to 100 gigahertz. Above that, it gets worse. There is so much that is not modeled in schematic that you will always have that discrepancy, I think. Then there's the difference between extracted layout and measurements. That's actually a lot worse, because if you want to fix that, that takes tens of thousands of euros and many months of waiting. And so that is something we really want to avoid, but we consistently see. It always happens. No matter how good the extraction, no matter how good the tools, no matter how good the models, there's just so many things we don't model accurately. Usually a lot of effort goes into modeling the silicon itself, but the environment, that is something that's much harder to model, also doesn't fit very well with the tools that we use. The cooling of the PCB, the parasitics, the coupling between the bond wires, all these things that happen in the periphery of the IC that affect the performance, that can have a huge impact to the point where things don't even work anymore. That is why we insist on making silicon, and that's also why, in industry also the experience is that first time right silicon is a nice myth, right? But if that happens, then you have not been ambitious enough. If you really make something that's ambitious, that's meant to compete with your best competitor, that's meant to make a breakthrough in performance in the scientific world, you need to push things to the limit. And that means that there are so many things that you need to model that you never get it complete. You always get missing things, and you need multiple silicon iterations, 2, 3, 4, sometimes many more. One of the projects I've seen in the past, we had 13 silicon iterations, but I'm trying to forget that one. And these differences, like I said, they can go from just a few dBs, right, 1.5, 2 dBs, for a very good design, all the way to being completely non-functional, oscillating, heating up to the point where it completely drifts. The synthesizer doesn't lock anymore because the varicap is giving capacitance that is so different at higher temperatures than at lower temperatures, and or heat waves that propagate along the surface of the chip when you switch on the PA. All these things happen, and all these things we don't model in the typical design flow, even with tools like Cadence. So you need to make chips, and you need to be prepared that your chip initially will not do what you expect it to do. The one thing as a coach that I can do is try to prepare people and tell them that this is something they should be quite happy about, right? So the best thing that can happen to you is that your chip is not doing what you simulated or extracted from the layout, because then you're going to learn. If things happen exactly like you expect, then there's no surprise, there's no learning. So that's the worst possible outcome. Students don't believe the story, but I keep telling it.
Yeah, as a student, I can understand that it might be definitely frustrating to believe in something like this. Yeah. So moving on, the next question is, sir, is there any method that exists in which we can add two returned microwave signal which are returned from the same targets? I'm not sure if you got that. Should I repeat it once more?
Yeah, please.
Yeah, so he says, is there any method that exists in which we can add two returned microwave signals which are returned from the same targets?
So that I understand the question is whether there's a material, whether you can have two microwave signals entering that, and then what should happen there? Should they mix, or what do they in that material?
I guess he's asking for to them get reflected by something, and then if we can add them up. So let me ask him to rephrase if possible, and then we can take up his question. So
yes,
Dr.
please.
Niranjan Kumar, if you can rephrase your questions in any way, we'll be happy to take it up. So till then, we'll. Yes, Professor, you can take your time if you want. Yes, Professor Baltus, you can take your time with having a break of 1 or 2 minutes if you want.
No, I just took a sip of drink. I was talking too much.
Yeah, I understand.
Yeah, but
so yeah.
So in general there are structures that reflect signals that does exist, of course. You have, for example, reflectors, but they would reflect the signal in the direction where they came from. Right? And there are materials like that. You have metamaterials that can do all kinds of funny things to microwave signals coming into them, and you can even make what's nowadays quite popular reconfigurable intelligent surfaces, which are metamaterials where you can change local parameters to change the behavior. So there's a lot of functionality that you can do indeed with passive structures, if you want, on incident microwave signals. Adding them, in principle is possible. I mean, a very simple structure would be two antennas, pick up the signals, and then you have a passive combiner of these two signals, right? And then you can transmit it again. That's definitely possible. So a lot is possible, but it depends what you want to achieve.
Yeah, I hope it answers his question. So moving on, the next question is, which simulation platform is suitable for the design of millimeter wave frequency?
If I'm nasty, I would say not a single one. No, it's like with any tool, right? No tool is perfect. No tool will do the job for you. Not even ChatGPT. I tried it. I had ChatGPT design an LNA. It would not have worked, but nevertheless, it was a good attempt. So tools are just something you use, right? And the better you are, the better you understand the limitations of tools, the better your IC designs get. So I find professional tools are good enough to get circuits working after a few iterations if you make an ambitious design. And yeah, nowadays, realistically, Cadence is it's not a monopoly, but they have by quite some margin the largest market share in the world, right? So there's no avoiding them, because many foundries like TSMC or Global Foundries or everybody provides their process development kits in Cadence format. So either you use it or you don't make a design. And unfortunately, that's the way it is. And you can live with Cadence. Many people hate it, especially our students. Initially, there's a steep learning curve. It's unfortunate. It's not the easiest of tools to get into. It's very powerful. It can do a lot of things. But if you're not an experienced user, you also can get out just about any result that you want, right? I mean, it doesn't have to necessarily have any link with reality. It's very much a tool where, yeah, you get out what you put in. You need to know what you're doing. You need to choose the right simulation. You need to choose the right parameters. You need to, and if you do everything right, you still get the wrong answer, but still something that's reasonably close to reality. But it would be nice to have better tools, yeah. Cheaper as well.
Yeah, I guess we all struggle with getting into tools and making the best out of them.
Yeah.
So yeah, the next question is, can you use the backside of the silicon die as a capacitor to further shrink die area?
In theory, it could be done. I think the problem is that for the standard technologies that we use, where we use nowadays mostly standard CMOS, so digital CMOS if you want, right? And there we don't have access from the circuit to the backside of the silicon. So through silicon vias, they're not standard in the type of technologies we use. So in theory, you could do things with the backside, but in practice we cannot. That might change in the newer technologies. So where you have the buried supply lines and through silicon vias, you might be able to do more. And if you really could optimize the process in the past, and there's been a lot of work and still ongoing on making very dense capacitors, for example, for DRAMs or for even high density solid state capacitors or solid state batteries nowadays, where you make very deep trenches. And you make sort of a 3D capacitor that goes into the depth of the silicon, really using the volume of the silicon rather than the surface. So if we had access to that technology and that technology would support good high frequency transistors, that would be great.
Thank you, Professor. And the next question is there any position open for MS and PhD in your lab? Kindly guide us how to apply and prepare.
So is there any op-amp?
Is there any position open for MS and PhD in your lab?
Yeah. We have many positions open. Okay, so in the Netherlands, a lot of the research gets funded directly by industry, and about an equal amount of research gets funded by the government, or either Dutch or European. That means that a significant part of my job consists of begging for money, right? And it's a sort of a lottery process. It's very random. So the idea is that on average, maybe 10% of your applications get approved. So you put in 10 times as many applications as you need. And what happened 2 weeks ago is that 2 of the largest proposals ever that we submitted got approved simultaneously. So now we have many positions opening up over the next 6 months. And there will be mostly in the area of radar, MRI, ultrasound, and 6G. There's a website, I can send a link later, where we publish the vacancies when they open up. But usually we know a little bit in advance when they're going to become available. So you can also send me an email, and then if you refer to this presentation, say I'm specifically interested in this topic or so, I can probably tell you, there's going to be positions in next month or in 3 months or whatever. However, maybe as a warning, right? Eindhoven is, and the Netherlands is not quite as nice a country as India. Our weather is miserable. People here speak Dutch. So maybe you want to talk to some of our Indian colleagues so that you know what you would get yourself into. But you would be very welcome from our side. I mean, that's not the point, right? But yeah, it's different.
So yeah, I guess people can reach out to you through the official website of the Eindhoven University.
Yeah.
Yeah, the mail present there might be the way to reach out to you about any of the inquiries they have.
Yeah. Yes.
Okay,
yeah. So I will send then the link to the positions, and if people ask about a specific topic, I can give an indication when they will become available.
Yeah. Okay. Sure, sir. So moving on to the next question, what technology node have you used for designing 60 gigahertz circuits? Any significant challenges faced while designing circuits at 60 hertz compared to the low end RF frequencies like 2 or 4 gigahertz?
Yeah, so the first 60 gigahertz designs we did in 90 nanometers. Nowadays we also we have done them in all the intermediate nodes, and now we are at 28 and 22, 28 bulk and 22 FDSY mostly, and we do some of that work also in the BiCMOS process from NXP. It's called Cubic, and it's something very different from the mainstream digital. And the lithography is not as advanced, but it's really optimized for RF. So suddenly you have really good models of your components, also the passives and so on. It has some benefits there as well. So yeah, is there anything different in designing for 60 gigahertz rather than for lower frequencies? Yeah, you have less gain from your transistors than at lower frequencies. Your passives tend to be lousy. Inductors, they're either tiny or they're a capacitor. Capacitors tend to be mostly resistors. And varicaps do strange things, mostly dissipate power. So it really, and if you make transmission lines, then you lose about 1.5 dBs or so per millimeter, right? I mean, it really adds up. So yeah, it is different from lower frequencies. You're mostly worried about all the things that don't do what you want to do. And I think eventually it gets better with better technology, but eventually if you go to the limits of the technology, it requires a different mindset. You have to give up on the concept of ideal components, right? That you design with something that you draw as an inductor or as a resistor. These things don't exist. And starting your design from these ideal concepts at some point is not becoming very helpful anymore, because what you have in reality is so different. So it requires the mindset that you start out from scratch thinking about, okay, I have some things that don't even look like resistors or capacitors or transistors, but they do something and I have a vague idea what they do. Can I make what I want with these very imperfect building blocks? And that is very different. If you go to even higher frequencies, currently the Fmaxes that top out at 300, 350 gigahertz. So if you currently are most of our work we do at 140, 150 gigahertz, that means you have almost no gain anymore. And so a lot of effort goes into making gain. And then you get things like, for example, you can get maybe theoretically 3 dBs of gain out of a transistor. With matching and biasing and so on, that might still be 1.5 or 2 dBs. Then if you want 10 dBs, you put 5 to 10 stages cascaded. But if you put 10 stages cascaded and your models are off by 1 dB for every stage, then you lose 10 dBs in total, right? So that also means if you have such a poor performance of your transistors, the accurate modeling of everything, not just the transistor, becomes really, really important. And I still think every day that it's funny, right? If you look at the transistor, beamformer model has more than 250 parameters for a single transistor. And then in the schematic, we connect these transistors with ideal wires that are zero length, zero resistance, zero capacitance. What's the point? I mean, what's the point of modeling a transistor so accurately if then you don't even model things that have at least a big an impact on the total performance as a transistor? So it really requires a different mindset, and the higher up in frequency you go, the worse that gets. But it's fun again, right? It's when you're young, you play with Lego, with ideal building blocks, and at low frequencies for audio, and then you get to know how things work. But at some point, you want more excitement, more challenge. And at these frequencies, you find it. You have now building blocks that don't fit, that have very weird shapes, that do very strange things. But once you understand that, you still can build useful stuff.
Yes, sir. Got your answer. Just a moment. Yeah. So the next question is, designing of RFICs is okay, but how to satisfy the power requirements of them? As per my knowledge, RF devices need large power.
Yes. Well, yes, they do. The trick is, why do they need power? Right. So I think that's how it starts. Some of the power is fundamental. If you make a transmitter, then transmitter needs to send to transmit 100 milliwatts. Then yeah, your circuit is going to take at least 100 milliwatts and probably a lot more. But it starts out by thinking, what is really the fundamental limit? What is the minimum power that I really would need to generate this function? And then separate the fundamental power requirement that you need for the function from the non-idealities, from the inefficiencies of making an actual implementation. The fundamental things you can only change if you change the system. So if you find that the fundamental requirements, so your transmit power, your linearity of your receiver, any of these require a power consumption that's more than you can accept, then you need to change the system. But if the fundamental requirements are good, but your implementation is very inefficient, and often it is, right? I mean, millimeter wave power amplifiers that are somewhat linear quickly get an efficiency below 10%, right? You dissipate 90% of the battery in heating up your amplifier, and only 10% goes out of the antenna. There is something you can do at the circuit level. And so it starts out with that understanding. Do I need to change something at the system level, or can I also do something at the circuit level? And then once you understand that, you need to think about, what can I do? I've mentioned some things like switching the circuit off, wake up receivers, TDMA, TDD, all these kind of things. Switching things off is a really good way to save power. Adaptivity, making sure that all your power, if you make a PA, right? If you make a phased array, you can direct the power in the right direction. That has two benefits. You need to transmit less power to get the same signal at the receiver, and you create less interference for other people. So making your array larger in some way to make a smaller beam is also a way to save power. So there are things you can do. At this moment, usually it gets done only when it's needed. If it's an industry, people in industry, they're there for making money, right? So they only do that when there's a risk that they lose money if they don't do it. At universities, we tend to look a little bit further ahead because we are not so much about making money, but trying to solve future problems. And there you see there are things that we can do, and you also see that companies do pick that up once you have solutions like that. And a lot is still possible. But there are some fundamental things that are not so easy to solve. I think in the end, what we will see is that the average range of wireless devices will get smaller and smaller, because ultimately the thing you cannot do much about is that still part of your signal gets sent in the wrong direction, no matter how narrow your beam is. And that means that a simple solution is just putting things closer together. So what you see with 5G, for example, is that we get base stations that are smaller, that have MIMO, that have lower power. And in that way, we can save the total power dissipation as well. So there's a lot we can do. And I think that's one of the things that make this area exciting. And I think the time to do that is now. For a while we were working mostly on mobile phones, initially there was a lot of pressure on the RF circuits because we were the main source of power dissipation. Nowadays, with the screen, with the processors, with the cameras, with everything, the radio is a little bit less dominant, but you see new applications coming up. You know, the AirTags, the small headphones, earphones, things like that, small sensors, where battery life suddenly becomes dominated again by the radio. And I think the pressure on finding better ways to make radios low power, that will continue.
Yes, so we will be taking just a few more questions now because we have gone way past our time and there are still questions piling up. So the next question is, sir, what would be the insertion loss for CMOS-based active inductor or transformer?
Oh, active inductor. Oh, yes, we tried that. It's not easy. So we have a design I have not talked about, but we're working on an RF FPGA. So one of the things is that we really would like to give our students this experience, even in the bachelor and the master, of seeing the difference between simulation and measurement. But having every student make their own chip, at the cost of tens of thousands per chip, and multiple iterations before they get it right, that's just not feasible. So what we have designed, in fact, Carlos Mendes da Costa Jr., the guy from the shock absorbers, he designed that as a sort of a side hobby. He has a design with many transistors and differential pairs in configurable widths and configurable bias currents and so on, and programmable inductors and programmable resistors, programmable capacitors, and the programmable interconnect array, so that you can make any circuit just programming the right bits of this chip. And everything works except the active inductors, because they're oscillators. It's really hard to get this right. The problem is that in the active part, you always have some phase shift, right? What you do is you make an amplifier. With the amplifier, you make a circuit that emulates an inductor. But if that amplifier has phase shift, and it always does at high frequencies, then your inductor gets a real component. Depending on how you do it, that can be a positive real component, which means it's a lousy inductor, or it can be a negative real component, which means you have an oscillator. To get it just right across a wide frequency range and across a wide range of programmable values is really, really tough. But it can be done. And if you play it on the safe side, yeah, you can get quality factors in the microwave range, let's say 5 gigahertz or so. 60 gigahertz, well, we have not succeeded yet. We have made the oscillator, right? So, but yeah, I think that it should be possible, but it's really, really hard to get that right. At narrowband, you can do a lot more. Also, when you don't design a separate inductor, but you say, well, I'm going to have an LC tank anyway, to make an active LC tank, you can do also a lot more. But you need to do something, configuration, a calibration, something to make sure that in the way you use it, it's always stable. And if you succeed, then you will find that you have a lousy inductor that dissipates a lot of current, that's noisy, and that distorts the signal. But otherwise, it's an inductor, right? So this is a field, if you really want to do advanced research and do something that benefits the world, then making a good active inductor and by extension a transformer, there is definitely room for a lot of improvement there.
Yes, so now we will be taking our last question. Dear sir, what are the practical challenges in CMOIS amplifier design in VHF and UHF frequency band?
VHF, HF, okay, that has been a long time ago. We haven't done much in that area for many years. So I'm not 100% sure what the state of the art is there. Sorry. I think nowadays I would expect that at these frequencies with modern technology, I think if that's the assumption, then the design will become very much like analog design, right? You can assume that you have almost infinite gain out of a transistor. You can assume that components actually do what they're supposed to do. The parasitics of the interconnect is not so critical anymore. Your wavelength is much larger than your chip. Yeah, so I would think that maybe there the challenge might be, if I would be guessing, but I really would be guessing, maybe there it's more in the linearity and interference, because at these frequencies they are so crowded nowadays that it might be hard to get the linearity you would require. But that's really just a guess. I'm sorry, I do remember VHF and UHF design, but that was really back in the Stone Age.
Yeah, thank you very much for answering all the questions. There are a few more remaining, but I guess those are more general questions. And I guess this gives us the indication that we should host you again sometime soon. So, yeah.
Yeah, thank you very much for the invitation and for this opportunity. And I'm always happy to try and answer more questions or anything I can help with. For me, this is really interesting to meet people in this way and to have discussions. So thanks again, and have a nice day.
So we are not yet done, sir. So yeah, there are questions and requests in this chat box where people have been asking about the recordings of the session. So what we generally do is we share the recording with these participants and the other audiences of our society as well through our YouTube channel. So shall we go ahead with the same for this webinar as well?
Sure.
Yeah, so there you go, people. The recording of this lecture will be there in our YouTube channel a few days from now itself. So you can find it there. And last but not the least, we have this small token of appreciation from our end to Professor. And
thank you.
Yeah, we had a great time. We had great discussion. This is perhaps the longest Q&A session that I have ever witnessed, and it's really nice to see you taking the time and the patience to answer all of these questions and share your vast experience and knowledge. So thank you very much, Professor. It has been a great experience.
Thank you very much, and thank you also for the certificate. I really appreciate it.
Yeah. Okay, and a huge shout out to all the attendees as well. You have made this webinar very successful. So hope to see you all soon. And thank you very much, Professor, again. Lot of gratitude from IFC.
Thanks. Have a nice day.
Yeah,
Bye.
Have a nice day.